Good morning, guys. So today we will see one example related to your vibration analysis. Okay. So in previous lecture we have studied this equation. Okay. We have got this equation after applying the boundary conditions. We will get this such type of equation. Actually, this equation includes a double derivative with respect to time and its a displacement. Okay. Double derivative, two times derivative of this displacement with respect to time. This term is nothing but your dou square u by dou t square, and this is nothing but your displacement. Okay, so such type of equations will be solved by assuming one solution. Okay, by putting the solution into this LHS side, you will get RHS side. Okay, so such type of solution is used in previous lecture. We have used such type of solution, and it is nothing but this vector u is equal to vector x times e raised to power lambda t, or you can say vector x times e raised to power I omega t, or you can put e raised to power minus I omega. Okay, so if you by putting e raised to power I omega t or minus I omega t, you will get the same solution. Okay, so we have selected this solution, that is u is equal to x into e raised to power lambda t or x into e raised to power I omega t to solve this type of equation. Okay, because by putting this equation you will get LHS is equal to RHS. It means what? This equation is satisfying this equation actually. This okay, so we have selected this such type of solution. So by putting this solution into this equation, we will get, okay, so if we put instead of u x into e raised to power lambda t, then we will get u dot as x into, instead of lambda t, here we will do I omega. Okay, so first derivative of this with respect to t, because this is with respect to t, so we need to take derivative with respect to t. So this will become I omega e raised to power I omega, and double derivative with respect to, so u double dot will become x times I omega into I omega e raised to power I omega. So this will become finally, so u double dot will become equal to x times I into I square into omega square into e raised to power I omega, where I square is nothing but minus 1. Okay, so minus 1 into omega square, it is nothing but minus omega square e raised to power I omega t. Okay, so put u is equal to x e raised to power I omega t, and u double dot is equal to x into minus omega square e I omega t into x into this equation. So we will get, so by putting this we will get, so instead of u double dot and into this minus omega square e raised to power I omega t into x plus, instead of this u, this will become e raised to power I omega t into vector x is equal to 0. Okay, now we need to simplify this step now. So what we will get, e raised to power I omega t, e raised to power I omega t, this is a common to these both terms, so this will get 0, which will be transferred to RHS side, so this will become 0. So finally we will get minus omega square into M matrix into x vector plus k matrix into x vector is equal to 0. Okay, so in this way we will get this equation. So this x vector is common, so we can write this equation as k matrix minus omega square into M matrix into this x vector is equal to 0, and this is nothing but your characteristics equation. Okay, now by using this characteristics equations we will get the omega values, that is frequency, this omega values will frequency values. Okay, so how to solve this equation. So such type of characteristics equation can be solved by assuming the determinant of this matrix equal to 0. Why? Because this x vector, the value of x vector is in non-zero, or it should be in non-zero values. So to have this non-zero values, we need to put the determinant of this matrix equal to 0. So determinant of this characteristics equation k minus omega square times and it must be equal to 0. Then you will get the values, that is omega values. You will get 1 or 2 omega values by putting this the determinant by putting this determinant equal to 0. You will get this omega values 1 or 2. Okay, that is characteristics equation. It means we will get the roots of this equation by putting this determinant equal to 0. We will get 2 roots. By using 2 roots, we will get the frequencies finally. Okay. So in this way, we need to proceed to solve or to get the frequencies of the problem. Okay. So now we will try to solve one example. Okay. So we will try to solve one example. So from this equation here, we can conclude that the coefficient of stiffness matrix must be equal to 1. To have some simplicity, we need to know that the coefficient of stiffness matrix should be equal to 1, and coefficient of M matrix here is the minus omega square. But from this equation, the coefficient of this K matrix should be equal to 1 for simplicity. Okay. So here we will solve one example. So example is what? Okay, for a uniform cross-sectional bar of length L is equal to 1 meter. Uniform cross-sectional bar of length 1 meter made up of material having Young's modulus E is equal to 2 into 10 raised to power 11 Newton per meter square. 2 into 10 raised to power 11 Newton per meter square, and density rho is equal to 7,800, and density is also given 7,800 kg per meter cube. Okay, density is also given. Cross sectional area A is equal to 30 into 10 raised to power minus 6 meter square. Estimate the natural frequencies of axial vibration of bar using both consistent and lumped mass matrix. Use 2 elements. Okay, here the diagram it is given like this. First or left end is fixed and we need to take 2 elements. Okay, so first, second and third element. Right end is free. Okay, so find out the natural frequencies of axial vibration or of bar using both consistent as well as lumped mass matrices. So using both conditions, that is by using consistent mass matrix and by using lumped mass matrix system. Okay, and use the 2 elements for this analysis. Okay, so as we know that the characteristics equation, it is given in this format. So for this case, we need mass matrix as well as we need stiffness matrix. Okay, and this equation is after applying the boundary conditions. Okay, so before applying the boundary conditions, this equation will be like, there are some boundary conditions like EA dou E by dou x and EA dou E by dou x. But after applying the boundary conditions, we will get this vector is equal to 0. Okay, so we will solve this equation by using these 2 elements. This is first element and this is second element. It means what? We need to write down or we need to calculate first mass matrix for both elements. Similarly, stiffness matrix for both elements. Okay, so first we need to find out the mass matrix for this first element as well as for second element. As the properties of these 2 elements are equal, so we need to find out the mass matrix only once. Similarly, we need to find out the stiffness matrix only once. Okay, so as we know that by using this consistent mass matrix system, first we will solve this equation by using consistent mass matrix system. So as we know that for consistent mass matrix system, the mass matrix is given by, so for consistent mass matrix this is given by equal to rho into A into L. This is equal to rho into A into L divided by 6 in bracket 2 1 1. Okay, so here length, total length is given equal to 1 meter. So for this first element this will become equal to L by 2, this will become equal to L by 2. So for first element length is L by 2. So if we put, instead of L we need to put L by 2. So L by into 2. So this will become rho into A into L divided by 12 in bracket 2 1 1. Okay. So this is the mass matrix for first element. Similarly, this is also mass matrix for second element. So global mass matrix will become equal to, so global mass matrix will become equal to rho into A into L divided by 12 in bracket 2 1 1 2. So this will become plus 2 1 1. So finally this will become equal to, so global mass matrix will become equal to, so this will become equal to, this global mass matrix will become equal to rho into A into L divided by 2 in bracket 3 by 3 matrix 2 1 0 1 4 1 0 1 2. So this is the global mass matrix. Similarly, we need to find out the global stiffness matrix. Okay. So as we know that the stiffness matrix K, it is given by, so the basic formula for this stiffness matrix is AE by L, AE by L in bracket 1 minus 1 minus 1 1. So the stiffness matrix also same for both elements because all the parameters are same. So length of this first element is L by 2. So we need to put, instead of L we need to put L by 2. So this will become 2 times AE by L in bracket 1 minus 1 minus 1. So global stiffness matrix will become, because there are two elements, so global stiffness matrix will become, so this will become global, it will become, this is a 3 by 3 matrix. So this is plus 1 minus 1 minus 1 plus 1. So this will become 1 minus 1 0 minus 1 2 minus 1 0 minus 1. So we can write this global stiffness matrix. This is equal to 2 times A into E by L in bracket 1 minus 1 0 minus 1 2 minus 1 0 minus 1 1. Okay, so in this way we will get the global stiffness matrix. Okay, now we need to write down this global equation. So as we know that the global equation it is given by, this is given by K matrix into X minus omega square into this M matrix into X is equal to the boundary conditions. Now we need to apply the boundary conditions at each node. So at each node, first node is fixed. So for fixed boundary conditions, we need to write down minus dou u by minus EA dou u by dou x. For second and third node, these are the free. Because if we write down for first node, as we know that for fixed node, it is written as minus EA dou u by dou x, and for other remaining nodes, it should be equal to 0. Okay, so we need to write down this global stiffness matrix as (1 minus 1 0 minus 1 2 minus 1 0 minus 1 1 into x, it is nothing but x1 x2 and x3. Okay, minus, okay, into 2 into A into L by, here we will write down this So K matrix is nothing but 2 times A by L, 2 times A E by L in bracket 1 minus 1 0 minus 1 2 minus 1 0 minus 1 1 into x means x1 x2 x3 minus omega square into this M matrix. M matrix is rho into A into L divided by 12 actually. Rho into A into L divided by 12 into this matrix. This matrix is nothing but 2 1 0 0 4 1 0 2 1. Okay, so in this way 2 1 0 0 4 1 0 1 2. Okay, so this is the mass matrix into this x vector x1 x2 x3 is equal to first one is fixed one, so we need to write down one representation for this minus PA dou u by dou and remaining equal to 0. So by applying boundary conditions here, this is only unknown value, so we need to eliminate first row and first column. So we need to eliminate first row and first column. Similarly here, first column. So finally, after this we will get 2 times A E divided by L in bracket 2 minus 1 minus 1 1 into x2 x3 or you can say into x. Here after applying the boundary condition, this will get equal to x minus rho into A into L into omega square divided by 12 in bracket 4 1 2 1 into x is equal to 0. Okay, this is 0. So in this way you will get this simplified equation. Okay. Now as we know that the coefficient of this stiffness matrix, it should be equal to 1. So we need to divide this equation by 2 times A into E by N. So divide, to make the coefficient of stiffness matrix is equal to 1, we need to divide by this term. So divide 2AE by N. So divide equation 1. Suppose this is equation 1. So divide equation 1 by 2 times A into E by N. So we will get this as 2 minus 1 minus 1 1 into x vector minus, if we divide this rho into A into L omega square divided by 12 into 2 times A by L. Okay. To divide, we will write down this here 2 times A into E divided by L into this matrix 4 1 1 4 1 2 1 into x is equal to this 0. So by dividing this, so we will simplify this, we will get A will get cancelled, L, this will get L square, so rho into L square into omega square. So L will get to the numerator, so it will get rho into L square into omega square, rho into L square into omega square divided by 12 into 2, 24 times 12 into 2, 24 times E. Okay, so this is the value. So we will write down the value rho into L square into omega square divided by 24 times E. Okay, so if we put this value, for simplicity, if we put this value equal to if we put this value equal to suppose lambda alpha, if we put instead of this value is equal to alpha, we will get final equation as into x. So here it will become alpha, this will become minus alpha, or you can say if we multiply this alpha to this value, this will become 4 alpha. So this will become 4 alpha, alpha, 2 alpha and alpha. Okay, because 4, 1, 2, 1 into x is equal to 0. So finally this x vector and x vector is common. So we can write down this as 2 minus 4 alpha. First term will become 2 minus 4 alpha minus 1 minus alpha minus 1 minus alpha and 1 minus 2 times 1 minus this alpha. Here 2 alpha minus 1 minus 2 alpha into x is equal to 0. Okay, so as we know that how to solve such type of equations to get the non-trivial solutions, it means what we need to have this vector as a non-zero value. So to have this vector as a non-zero value, we need to put determinant of this vector is equal to 0. So determinant of this vector is 2 minus 4 alpha minus 1 minus alpha minus 1 minus 2 alpha 1 minus alpha is equal to 0. Now to solve this determinant, we will get this in this minus multiplication of this minus this. So 2 minus 4 alpha into 1 minus alpha minus 1 minus alpha into minus 2 minus 2 alpha is equal to 0. Okay. So on simplification, by simplifying this equation, we will get one quadratic equation in terms of lambda. So by simplifying 2 minus 4 alpha into 1 minus 2 alpha minus 1 minus alpha minus 1 minus 2 alpha. So by simplifying this, we will get one quadratic equation as 7 alpha square minus 10 alpha plus 1 is equal to 0. And if we solve this quadratic equations for two roots, we will get alpha is equal to 2 and alpha first one is equal to 1.32 and second one is equal to 0.10. Okay, so we will get these two values. Alpha is equal to 1.32 and alpha is equal to 0.108. But as we know that alpha is given, instead of alpha we have actually put alpha is equal to rho into L square into omega square divided by 24 times. So as we know that alpha is equal to this, so this will become 1.32 is equal to rho into L square into omega square divided by 24 times E, or 0.108 is equal to rho into L square into omega square divided by 24 times. So by solving this, or by putting all these values, as we know that density is known, length is known, E times modulus is also given. So by putting all the values, we will get omega is equal to, first omega is equal to 28501.012, or second omega you will get is equal to 8512.815.39. Okay, so this is you will get two values of omega, and the frequencies are given by equal to, frequency is nothing but f is equal to omega by 2 pi, or here f is equal to omega by 2 pi. In these values you will get first frequency as equal to 4536, or second frequency as 1297.1 Hertz. Okay, so in this way you will get these two frequencies, that is frequency of first mode is equal to 4536 Hertz and of second mode is equal to 1297 Hertz. Okay, so in this way you will get these frequencies. So how this is the example in which we have applied our vibration analysis process to get the frequency values. Okay, so in this way you can proceed. Okay, so here I am concluding this lecture, and in next lecture we will see some another example. Okay, so I am concluding this lecture here only. Thank you.